This video will give you an overview of printability maps in the additive manufacturing module in ThermoCalc. Printability maps, which are also known as process maps, were introduced into the software in ThermoCalc 2024b. They allow users to predict the likelihood of 3 possible defects that occur during the powder bed fusion process in additive manufacturing: keyholing, lack of fusion, and balling. In the video, I'll briefly discuss what printability maps are used for. Then I'll discuss the criteria we use in our software for the defects. Finally, I'll show you how to set up a simulation in the software, and I'll discuss the results. If you have a license for ThermoCalc 2024b or newer and the additive manufacturing module, you can follow along in setting up the simulation, regardless of which database you have. Otherwise, you can simply watch the video to learn about this powerful feature. In additive manufacturing, machine fabricators need to create printability maps experimentally when they use a new material. This is done in order to find the processing conditions that are viable for printing. Basically, you create a grid of experiments by varying the power and scan speed for each cube to get a real-life map of the results. The printability map shown on the screen is a 6x6 mesh. For each point in the mesh, a cube was printed, polished, and then the porosity amount was measured. When you combine the results from all 36 experiments, you can see a map of the porosity. So in the lower right corner, where there's high scan speed and low power, we can see uneven porosity due to the powder not melting fully. And this is called lack of fusion. And in the top left corner, you have high energy density, which is high power and low scanning speed. And with this combination, you fully melt the powder, but you get keyholing and keyhole porosity. It's only in the center region where you have a fully dense material with little or no porosity. The idea with the AM module is that we want to reproduce these printability maps with simulations rather than with experiments. We do this by running many steady-state simulations that vary the power and scan speeds. For each simulation, we get the melt pool size and keyhole size. We then formulate criteria to define when the various defects occur. Let's discuss the criteria we use for the defects. We'll start with the lack of fusion criteria, which we had in the bottom right corner of the experimental printability map. Lack of fusion occurs when the depth of the melt pool is shallower than the depth of the powder thickness, so not all of the powder melts. So the first criteria is that the melt pool depth is greater than the powder depth. And this is for a single track. But when you print a material, you print multiple tracks that are separated by a hatch distance, so you can also get porosity and unmelted powder in the middle between the tracks. So we also look at the depth between the 2 tracks at half of the hatch distance. And for that, we have a second lack of fusion criteria that requires that the depth at half of the hatch distance should be greater than the depth of the powder thickness. And both of these criteria are available in the software to view on a printability map, which we'll do in this video. The second defect we encounter is this round keyholing porosity, which we saw in the upper left corner of the experimental printability map. And this happens at high energy densities. It can be seen experimentally that the frequency of these pores increases with the keyhole depth. We can see the keyhole porosity here in the image. So the defect criteria we formulated looks at the ratio of the width to the depth of the keyhole. As an alternative criteria, we use the width and depth of the melt pool dimensions, which is more common in the literature, but it should only be used if you have a heat source with no information about the keyhole geometry, like a volume heat source. The default in the program is to use the keyhole geometry, which is what we'll do in this video. Finally, the third defect is balling, which occurs at high scanning speeds. Here, instead of a nice smooth track, you get agglomerated particles due to poor wetting and surface tension effects, which form droplets on top of the surface. In literature, people have related this defect to the melt pool dimensions, either looking at width divided by length or depth divided by length. So those are the 2 balling criteria available in the software. But we won't be looking at those in this example. So to create a printability map, we need to create a lot of steady-state simulations, which can be done in two different ways in the software. The first way is to run a batch type calculation, where you read in a list of power and scan speeds. Optionally, you can also include the experimental width and depth of the melt pool. The other option is to create a grid calculation, where you set a range for power and scan speed. And this is the preferred option for printability maps because you get full coverage of the plot area. If you use the batch calculation and only base it on experimental conditions, they often leave out the most extreme cases, so you get areas in the printability map that are blank. So we recommend that for a nice printability map, you use the grid calculation type, which is what we'll do in this video. The simulation we're going to set up is for a 316L material, and it's based on a paper that examines the influences of the process parameters on a single track. For the simulation, we'll use a Gaussian beam radius with a fixed size of 22 micrometers, a constant powder layer thickness of 10 micrometers, and absorptivity of 30%. The calculation is based on example AM, 09, A, and B, which are included in your software. So you can run those if you'd like, rather than setting up the simulation manually. But in this video, I'll walk you through setting up the simulation, and then we'll discuss the results. If you just want to see the discussion on the results, you can skip ahead to the results chapters of this video. To begin setting up the simulation, open ThermalCalc in the graphical mode. There are two AM templates on the home screen. The first is for calculations that will generate materials property data from a Scheil simulation, and the other is for calculations that use a materials library, either a library that shipped with the software or one that you created and saved. We'll be using a materials library that shipped with the software, so click the With Material Library icon. First, we'll select our material library, so click on the Material Properties tab. From the drop-down menu next to Library, select SS316L. This is a materials library that ships with the software, so anyone with a license for the AM module can use it, even if you don't have the database it was built with. We can see that it was created from the TCFE13 database and uses the iron alloy shown on the screen. If you'd like to, you can select various properties from the Plot drop-down menu to see the plot results. But we don't need to do anything else in this tab, so we'll go back to the Conditions tab to set up our simulation. We're running a series of steady-state simulations, so we'll keep that calculation type selected. Since we're running a grid calculation, go ahead and scroll down and select that option now to get all the fields for the calculation. When we select grid, we can see that a range of power and scan speeds appear, so we'll set those now. Set the power from 40 to 100 and leave the number of steps as 5. Set the scanning speed from 400 to 3000, and again we'll leave the number of steps as 5. Now we'll return to the top of this section and we'll accept the global settings as they are. We'll also leave the geometry as it is, with a height of 2 millimeters and coarse mesh. For the heat source, we'll use Gaussian with an absorptivity of 30% and a beam radius of 22 micrometers. We'll also use the keyhole model, so go ahead and check that box. And we'll accept the default value for Rayleigh length. If your material and machine are different, you can change these to match your system. Finally, we'll set the layer thickness to 10 micrometers, and we'll accept the default values for all the top boundary conditions. Our calculation is now set up, so we'll go ahead and run it. Right-click on the AM Calculator 1 node and select Perform Now. Your simulation may take 30 minutes or more to run, depending on your system, so you can pause the video while it's running. Once the calculation is done running, click on the Plot Renderer 1 node to view the plot settings. We want a layer thickness of 10 micrometers, so enter that if it didn't propagate from the AM calculator. Now right-click on the Plot Renderer 1 node and select Perform Now, and your plot should appear almost immediately. The first plot we see in the visualizations window is the 3D plot, so we'll take a look at it. I'll click the Zoom to Heat Source button to get a better view of the melt pool. The glyph scale factor is quite large and makes it hard to see the melt pool, so before we look at the plot, I'll reduce that to 0.1 to get a better view. I'll also select only the liquidus so that we get a clear view of the depth of the melt pool, which is this green ring. I'll also select this icon above the plot that looks like a box, which shows the depth of the powder bed, which we've set to 10 micrometers. So now we can clearly see how close the melt pool is to the powder depth. If you expand the grid data drop-down menu, you can see all the power and scan speed combinations that were calculated, and they're sorted in order of energy density. We can see that at the first power and scan speed, there will be a lack of fusion because the melt pool is not as deep as the powder layer. If we return to the grid data drop-down menu and select the third data set, we can already see that the melt pool is almost deeper than the powder layer. And by the fourth set of data, the melt pool is below the powder layer thickness, so we shouldn't have lack of fusion anymore after this. As you keep going down the list, we get higher and higher energies, and you can see a keyhole start to form. And eventually there will probably be keyhole porosity and the collapse of this keyhole. For this particular material, the research showed that they got quite a deep keyhole at the high power and scan speeds, and we can see that reflected in the plots. You can also change the powder layer thickness here. For instance, we could look at a layer thickness of 50 micrometers. But this only works if you use the same materials property for the powder and the defined material, which you can see here that we did. So that's one way of looking at the results, where we look at the results one by one in a 3D plot. But with printability maps, we can also look at the combined results from all the simulations. So let's make a printability map and look at that. First, we'll rename plot renderer 1 to 3D grid so that we can tell the plots apart. Next, we'll create another plot renderer, so right-click on the AM Calculator 1 node, select Create New Successor, and then Plot Renderer. We'll rename this one Printability Map. The configuration window now shows the settings for the printability map. If you expand the Show Table button, you'll see all the simulations with power and scan speed, and the simulated width and depth of the melt pool. We'll close that and we'll set the hatch distance to 35 micrometers. The layer thickness is already set to 10 because we set it earlier in the calculation, so we'll leave that. As you can see, we have plot settings for keyholing, lack of fusion, and lack of fusion hatch, which is what we'll look at in this video. You can add or remove criteria with the plus and minus buttons, or you can change the criteria. But for our simulation, we'll keep these three criteria. We'll increase the lack of fusion criteria to 1.3, but we'll leave all the other settings as they are. Once everything is set, click Perform at the bottom center of the program, and your printability map should appear almost immediately. In the printability map, we can see keyholing on the left side, lack of fusion in the bottom right corner, and lack of fusion hatch just above that, which is similar to the experimental printability map we saw earlier in the video. In the center white space are the power and scan speed combinations that will minimize the risk of these defects. In the printability map, we can toggle Show Result Points on and off, which shows the points where we performed the simulations. We can also toggle each criteria on and off to focus on only one. So let's look at the keyhole first and toggle the others off. So here we use the criteria width and depth of the keyhole should be smaller than a value. And the value here is 1, which is the default. We can change these limits to capture experimental results, but the hope here is that these limits are fairly consistent between similar alloy systems, so you should be able to use the defaults in most cases. You can also visualize this with ISO lines, which we can toggle on for each of the criteria, and we can even change the number of lines. And when you toggle those on, you see the values along the lines for the defect criteria, which in this case is keyhole width divided by depth should be less than 1. Smaller values indicate defects, so as we move up and to the left in this region, the values get smaller and the likelihood of defects increases. You could also toggle the area plot off if you want to only visualize the ISO lines. And you could change the color of the area plot by clicking on it and selecting a color. Now let's toggle on the lack of fusion criteria, where the depth divided by powder thickness should be smaller than 1.3. And we can see this defect in the bottom right corner. If we increase the powder thickness, for example, to 25, we can see that this lack of fusion region increases, and the likelihood of defects increases. But let's put it back to 10. If you change the hatch distance, say to 50, nothing happens. And that's because we're looking at the single track, so there is no hatch. So let's look at the lack of fusion between the tracks. And now when we change the hatch distance, this lack of fusion criteria changes as well. And of course, the layer thickness also affects this region as well. And again, this criteria is depth at half of the hatch distance divided by the powder thickness should be smaller than 1. Optionally, you can also create your own criteria with the custom option by giving it a name and then using a combination of the melt pool dimensions combined with the hatch spacing and powder thickness. For example, you could define lack of fusion as a custom function, as I've done here. Users of the AM module can also import experimental data into the program, if you have it, and overlay it over the plot. To do this, right-click on the My Project node, hover over Create New Activity, then select Experimental File Reader. From the configuration window, click the folder icon, locate your file, and click Select Experimental File. Finally, right-click on the Printability Map node, hover over Add Predecessor, and select Experimental File Reader. Right-click on the Printability Map node and select Perform Now. Your experimental data should appear almost immediately. We've configured this data so that the green labels show experiments without defects, and the red labels show experiments that resulted in defects. As you can see, the experimental data closely matches the calculated results. I hope you found this video on printability maps in the AM module useful. We're creating a lot of content for the AM module, and the best place to find it is on our website at thermocalc.com, and then the additive manufacturing module page. All the content will be added to the bottom of the page.